Okay, good morning everybody, and welcome to the last session on ESP this semester. So last time we stopped at APC coding. So APC coding was using prediction to obtain a small prediction error, and then this prediction error is transmitted to the decoder. And we based the prediction on blocks of 20 milliseconds. So for every block of 20 milliseconds of speech, we compute our prediction coefficients, and then these coefficients are transmitted as a side information to the decoder. And this kind of system is used, for instance, in most digital cell phone systems. An example is adaptive multirate codec from the ITU, which is used in most cell phone systems. And so when we talk on your smartphone, it's most likely that this principle is used for the speech coding, the speech compression. So an alternative is the so-called least mean squares algorithm. And unlike the LPC algorithm above, which computes prediction coefficients for block of samples and transmits these coefficients alongside the prediction error to the receiver, the LMS updates the prediction coefficients after each sample, right? But based only on past samples. So that's a big difference. So we do it after each sample. And in order to be able to do that, it's based only on past samples. So, hence here we need the assumption that the signal statistics does not change much. And so it stays more or less constant. That's the assumption that we need to make here. So from the past to the present, there should be not too much change in the characteristic of the signal. So since it is based on the past samples, which are also available at the decoded samples, as decoded samples at the decoder, we do not need to transmit the coefficients to the decoder. Instead, the decoder carries out the same computations in synchrony with the encoder. Right. So we do the adaptation of our predictor in the encoder and also in the decoder. Remember, for LPC, the decoder just needed to read in the coefficients it obtained from the encoder. Here, it doesn't get any coefficients, so it also has to compute it. So this also shows you that the decoder is more complex in this case, because it also needs to update the coefficients. Yeah, instead of a matrix formulation, we use an iterative algorithm to come up with a solution for the prediction coefficients H, the vector which contains the time-reversed impulse response of our predictor. And to show the dependency on the time n, we now call the vector of prediction coefficients h of n. And so this is the vector h, capital H. So this contains, for instance, our 10 coefficients, and this changes over time. So in LPC it was the same for the entire block. So there we just needed a block index here, but here now we have the sample index. For each sample we have slightly different coefficients. So this is our vector then. Here we can see it contains the individual prediction coefficients independent of the time. So again, we would like to minimize the mean quadratic error function, prediction error, with the prediction error E equals x minus x hat. Right, so here we have x minus x hat squared, so this is our quadratic error. And then we compute the average, the expectation over it. And we know x hat is simply this sum here going over the past samples. So we have our weighted sum over the past samples containing our prediction coefficients. So now we can actually draw in the expectation. So to get a solution, so instead of using the closed form solution, which leads to the Wiener solution, we now take an iterative approach to to approach the minimum of this optimization function. Right? So basically we now view this here as the optimization objective function or error function, which we would like to minimize. Right? So instead of closed form solution, now we take a numerical solution with an iterative update. And for that we use the so-called steepest descent, also called the gradient descent. So here I have this Wikipedia link where you can read more background information on this. And it has this iteration towards this minimum. So in general, gradient descent takes the current state of our coefficients. It computes the gradient of our error function. So f is our objective function or error function that we would like to minimize. So in this case, f is our mean squared error of the prediction error. It's the mean squared prediction error. So this is the gradient, and this is the vector because h is a vector. Right? So f is a number, right? This average error that we get. But then we need to take the derivative of f with respect to each h. So that makes it a vector. So that's why we have a gradient. And the gradient has the same dimension as the coefficient vector h. And that's why we can actually take this difference here, because it has the same dimension. Make sense? So we take the old vector of coefficients and subtract an update vector, which consists of the gradient with respect to our coefficients times some constant alpha. And usually this alpha is some constant, usually some small number, and it's a tuning parameter for this kind of update, the gradient descent. Yeah, so we now take as our function to optimize the f as our squared prediction error. So this is now our f, right? So f is our error and depends on our coefficients at time step n. So here you can see it. This is how we defined it, right? And also note that I dropped the e here, right? So this is kind of peculiar, right? I just dropped the e, and it turns out it still works. So here we have now the hk. They depend on the time n, and again, this is our usual sum over the past samples. So here we omitted the expectation operator e for simplicity. We expect that after several update steps, there will be inherently some averaging going on, right? Because we do this often enough with small steps. Basically, these small steps over time accumulate, and hence they are doing the averaging for us. So this is also called stochastic gradient descent, right? Because we do the averaging over our update steps. And that actually simplifies our update, because then we don't need to compute the expectation for each update step. Right? We just look at the current samples and don't need to average over all the past samples. Strictly speaking, we would have to need to average over all the past samples, but here we just don't do it for simplicity. And it turns out it still works, so that's nice. Yeah, so using the stochastic gradient descent, we have this gradient, right? So we have the derivative of this function with respect to each of the coefficients. Yeah, and if we take, so this is the general formulation, and if we take stochastic gradient descent, then it simplifies to this one. So this is basically our derivative of this error function with respect to each of the coefficients. So this is basically the outer derivative. Remember we had e squared as our error function. function, and if you take the outer derivative, it's 2e, right? E squared, outer derivative is 2e. And then derivative of e with respect to h, the inner derivative, is this minus x of n minus 1 minus k. Right. Remember the e was simply the sum here. Here this inside the square is the e, and if we take the derivative of this expression with respect to xk or xj, then this disappears because it's not dependent on the coefficient, and what's left of the sum is just the j's entry here. Right? So here we have the desired variable to which we take the derivative, and this is the factor of it. So we just have one factor, which is this hj. Or here we call it k. So this k goes from 0 to n minus to l minus 1. So we can have that with k is 0, n minus 1. Yeah, makes sense? So simply outer derivative times inner derivative. So it's the chain rule of taking the derivative. So both together leads us to this update rule. So we have the new coefficient set consisting of the old coefficient set plus alpha times, now we have this stuff here, e times x. And remember before we had the minus, and if you combine it with this minus, we get a plus. So this is now our update rule here. And if you look at it, it's fairly simple. You simply have to take a look at the current error at the output of our predictor. So this is the current error. Then we multiply this error with a sample at the kth coefficient. So this is the input signal, the past input signal, which is multiplied by our kth coefficient. And this updates the kth coefficients accordingly. Right. So again, this goes from k equals 0 to n minus 1. And alpha is a tuning parameter. And I also absorb this factor 2 into this alpha now. Right. Since we have any alpha that's not really fixed, then we can also absorb this factor 2 into this alpha. Yeah, this alpha can trade off convergence speed and convergence accuracy. So if we have alpha large, then we have large steps, large update steps, so it converges quickly. But maybe it's too quickly because it can overshoot our minimum, right? So then we need to choose alpha smaller because then we slowly approach the minimum and we approximate it more precisely. Right. Yeah, and derivation or computation of the alpha value can also be found in the lecture slide set 15 of our lecture on microwave signal processing. So they actually derive the alpha, which you can do. So there is some optimum alpha, which you can obtain either by trying it out, letting it run and see if it works, or you can actually compute it, depending on this. Yeah, and you can also write this update formula in vector form, because on the left-hand side we have a vector, on the right-hand side we have a vector, so we can actually update it using the vector of past coefficients x. So here, the new vector of coefficients is the old vector plus our update, which simply consists of our alpha times the current prediction error, which is the number again, times this vector x. And this x simply contains the past L samples of our signal. And so this is convenient for an implementation, say in Python, because then we don't need a for loop or going over the coefficients. We just have two vectors which we need to add. So here the old vector of coefficients, and this is the vector of the update. Easy, right? So it's amazing that this works actually. So observe that we need no matrices or matrix inverses in this case, just this simple update rule, and it still works. It still converges to the correct coefficients. Well, at least usually it does. There's usually no guarantee. It can also diverge depending on alpha. You can imagine if you choose alpha way too large, then it overshoots and it's getting bigger and bigger. Right? That can happen. So for the prediction coefficients h, we have something like a sliding window of the past L samples x of our signal. So this is the vector we need for the update. So this should be alpha actually. So alpha. Yeah, so for alpha, there are different recipes. For instance, the so-called normalized LMS. It uses the inverse signal power as alpha. Right? So this is kind of an easy estimation for a good value of alpha. If the signal power is 1, then alpha can be 1. But in general, it is subject to hand tuning, trial and error. Yeah, so here I have a little example in Python. So you can see how we could implement it. So first we would start with the usual imports, our sound library from Moodle 2, here Matplotlib for plotting. Then here I'm using WOFRead from our sound library. You can also use scipy.io, which is doing the same thing. And I'm reading in here this fspeech.wof example file. So actually you could also use any other WOF file. It should always work. So for instance, you could take the microphone of your laptop and record your own voice. It also works for your own voice. So this WOFRead then returns the samples in X and the sampling rate in Fs. Then here I'm normalizing it and converting it to a type float. Right. So now this X contains the samples in the range between -1 and 1. And remember, this is connected to our alpha, and this is actually one of the reasons why I did this. Right? Because then this alpha becomes a nice number close to 1. Right? So if I don't do this normalization, then we would need to use this alpha, choose this alpha very small, like 10 to the minus 10 or something. So then I'm printing the size, basically to see the number of samples. And here I'm initializing our prediction error. So I want to see the prediction error at the end because I want to plot it. That's why I want to store it. Otherwise, you wouldn't need this in LMS. Right? Remember, you only need the error, the current error, for the update once, and then it's gone. So you don't need to store it actually. I just store it here for plotting purposes. So H is initialized with all zeros, our coefficients, our prediction coefficients. And here I'm doing the loop over every sample. So you can see I'm starting with sample number 10, because at sample number 10 I already have the 10 past samples. Right. So then I'm computing the prediction error and the filter using the vector of the time reversed impulse response of our predictor. So here is our current error starting with sample number 10. Here I have current sample number 10, and here I'm doing the prediction. So I have dot, the dot product is the matrix product. Here I'm flipping the X because I'm doing the convolution. Here I'm having the past 10 samples. So from n, basically the 10 past samples, so from the 10th sample in the past up to the present. So here the range, remember, goes up to 9. So it just didn't get the current one. And then I multiplied here with the prediction coefficients. Right? So this is our sum, going over the past 10 samples and multiplying it with the prediction coefficients. Can you see that? So this is our prediction sum here. So it takes the predicted value and subtracts it from the current value, and this gives us the current error. Yeah, and then I'm updating it. So after using the coefficients, I'm updating the coefficients according to the error that we obtained. And remember, now we have the error here, and we can use it to update our coefficients. So here you can see it, the new h. So remember, h is an array, a vector. Right here, it's a vector of 10 coefficients. So the new array is the old array plus alpha. Here I'm choosing alpha to be 1.0, convenient number, times e, this e here, times the past samples. So this is our array of past samples. And for convenience, I'm using the flipped version because I also use the flipped version here. I could also have to use the unflipped version and flip h instead. Doesn't really matter. So I'm going to compare it to our sum. Let's see, did I flip the h or did I flip the x? Here in the folder, there's the sum folder. Here's the sum folder. Yeah, so here you can see it. Here you can see the x is the flipped version, right? Because the k goes down. So this corresponds to this sum formula I use here. Here I'm using the x and the h is non-flipped here in this sum formula. So basically I'm using this formula here for the implementation. So that's why we have the flipped version of x. Yeah, that's basically all. Right? Those two lines here do the filtering and the update. There's no computation of a matrix A and no autocorrelation matrix, no matrix inverse. It's just those two lines. And that's what's so fascinating about this algorithm. It's so simple. This is a really easy update here. The only drawback is that we have to do it for each sample. Right? So we have to really update the coefficients for each individual sample. And then also, and that means we need to have this for loop over each sample, and that makes it a little slow. Right? So it's very easy to implement, but it's not necessarily fast. Right? So in an implementation, this can be slower than the LPC. Yeah, and then it prints the mean squared prediction error. So here we take this, after we are done with this loop, so here we are done with this loop, so all the signal is processed. So here we compute the power of the error divided by the number of samples. So we have the power per sample of the error, which is this number. And then we can compare it with the signal power. So we take x squared basically. So we multiply the vector by itself, transpose, divide by the number of samples, and this is the power per sample of the signal. Then we can divide those two to get the signal to error ratio, which is down here, and this is 32 in this case. And remember, for LPC we had 60 something. So that's about half as much as for the LPC. So why is it not so good? You constant updates, right? Unlike the LPC, which we do only once per block. Why is it less efficient? What do you think? Half as much.
Is it because of the length?
No, it's the same length. It's 10 coefficients, exactly the same as for the LPC.
Because it does it for every sample than for just a block.
Well, it should be better, right? Because it's always on time, sort of. You always have the optimum coefficients at this point of time. Well, but the optimality is actually the question here. Is it really optimal? When you compare it to the block computation?
Maybe because of the average. Maybe there's some, it takes error with itself along while it follows the signal.
No.
Something like that.
No. Also, remember this was the statistical gradient descent, so it actually takes some time to update, right? So this averaging needs time. So it's kind of slow. So imagine we have a change of your signal going from tonal to vocal, for instance, or to noisy. Then it takes some time to get to the new state, or from one tone to the other tone. It takes some time to get to the new state. So basically, in general, the coefficients that we get are good for the past. And that's the principle here, right? It's always based on past samples. And that's not necessarily what might be good for the future if the signal is changing. And that's the difference between LMS and LPC. In LPC, you have the optimal coefficients for the current block that you want to predict. Right? You not only have the past samples, but you also have the future samples in this block. Right? You have one fixed coefficient set, that's the drawback. It doesn't change over the length of the block. But if the block itself doesn't change much in the signal characteristic, then you have pretty good coefficients. And that's also why they choose 20 milliseconds as the length, because usually when you have speech, in 20 milliseconds it doesn't change much. So this assumption of the signal being more or less stationary inside this block is usually true. And that's why you get pretty good coefficients for this block. And that's different for the LMS. For the LMS, you can only look at the past. It's kind of slow updating, changing. And that means if you have a sudden change in your signal, it takes some time to follow, and in the meantime, you have a high prediction error. Right? And that's why you get less signal to error ratio. Yeah, but then on the other side, for LPC, basically this means you need more bits to represent this prediction error. Right? So this means this would be less efficient for compression. But on the other hand, here you don't need the bits for the site information, for the coefficients. Remember, for the LPC, we need to transmit the coefficients alongside the signal, and that increases the bit rate. Right? So for LPC, we also need a better prediction in order to make it worthwhile to transmit the coefficients as site information. Right? So there's a trade-off. If we have a signal which doesn't change much, then LMS might be better because we don't need the site information. If you have a signal which changes a lot, then it might be better to use LPC with the site information. Yeah, so here finally we can listen to the prediction error, and here we plot it in comparison with the original, so that we can see it. And here we can execute it. So let's do it. Copy. First let me open it with the editor. Here's our little LMS example. And you see it's basically the same that we just saw in the slides. Here, the only difference here is that this if print. In this sample range between 4000 and 4010, we're actually printing the encoder coefficients H. So 10 sets or 10 vectors of coefficients. And we will see in a minute why we do that. And here are the two lines, right? Here the prediction error, and here the update of the prediction coefficients. And then here's the computation of the error. So let's try. So run it.
So it's frequently a very difficult matter, and yet sometimes it's necessary to do so.
So what do you think? good. Maybe you can compare it with the sound of the LPC last time. So when we take the LPC example, here's the LPC example. First I have to close the figure here. Oh yeah, this is the reconstructed signal. What do you think? Yeah, before I play the LPC example, we have to look at the reconstructed signal of the LMS. Looks kind of strange, right? So this comes from, I'll show you the code. So here's the decoder. And basically the decoder is also doing the same as the encoder. So first, instead of computing the error, you compute the reconstructed signal, right? So it makes sense using the past reconstructed values and the current coefficients, and then you update the coefficients. So this should be done in synchrony with the encoder. And then it plots it and plays it back, and we didn't hear anything. But actually you actually hear it after I close this. So let's first take a look at what we see here. So here, horizontal axis is the sample number, vertical axis is the sample value. So looking at the values itself, it looks okay, but then you look at this factor here. Do you see it? 10 to the 193. So this is not right? This is way too large. And you get this large factor because here in the end, it basically explodes. And you can also see here, 15,000. This is not the end of our signal. The signal was maybe 200,000 samples long. It's just 15,000. So basically at the beginning, it explodes. So this happens when you have an instability, an unstable system. It explodes. This is how an explosion looks like. It's an exponential growth, which looks like all of a sudden there's this explosion. This is how it sounded. So in the beginning it was more or less okay, and then was gone. And now we can also compare the coefficients. So here I have the 10 coefficients in this range. So let's take a look at the last one here. So here you can see the last coefficients in the set, which is 4010 or 4009 here. So here we have minus 0.0618 for the decoder. And let's see what we have in the encoder. So minus 0.06186. Is that the same? Do the coefficients look the same? Maybe I'll go back. So memorize the number, minus 0.0618. 618. So here's a different digit here, right? So in the other one, this was also an 8, here's a 7. So that means they diverge. Right? So ideally, they should be exactly the same, those coefficients. But you have slight changes in those coefficients. And those slight changes here in some digit, like in the 5th digit here after the decimal point, they accumulate, or basically they exponentiate, they have exponential growth, those errors. Right? Because a slight error at one point leads to a larger error at the next point, and so on. Right? So the error becomes larger and larger, it grows exponentially, and then it leads to this catastrophic failure. Yeah, so I also wanted to play the LPC example.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So here was the error, and I guess you could hear that it's less for LPC.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So here's the reconstruction, and as a comparison, the LMS.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So you can hear that the error is larger. Right? There's more to hear from the original speech. And then here you have the reconstructed signal. So right at the beginning it's okay, and then all of a sudden it fails. Right? So why don't we have this problem with LPC? This failure problem. In LPC, remember, we transmit the coefficients to the decoder. That means we are guaranteed that the decoder has the exact same coefficients as the encoder because of this transmission of the side information. Whereas in LMS, the coefficients depend on the correct reconstruction of the past samples. So if there's one sample incorrectly decoded, that means we also will have incorrect age, which then incorrectly decodes the next sample, and so on. Right? It's the chain reaction. So what can we do to fix it? How can we fix this problem? This is actually a typical engineering problem. Something doesn't work, and you found the problem, the cause of the problem. Right? So
Shooting alpha.
how would that help with a problem?
You could either increase it or decrease it and try an error.
Yeah, but why should it help?
Maybe exceeded a minimum, or did it find some minimums? Maybe the gradient descent didn't work.
You know, it's possible, so we can try it. So, what do you want? Like point one?
Let's try.
So we can have 0.1 for the decoder and 0.1 for the encoder. 0.1.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
It sounded almost like the error became bigger, right?
Yeah.
So this is our prediction error. Do we have a display of the error here? Yeah, so here you can see it. The signature prediction error is now only 16. Right? Before we had 32. So this is now half of this ratio. That means the error is twice as big.
So then we go to 2.
First, we have to listen to the decoder if it fixes the problem, right? So we see our fix makes one property worse, right? But we have to see if it really fixes the problem. So this is the reconstructed signal. Actually, it looks good now.
It's an audio signal.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Very good. It fixed it. At least for this signal. The problem is you're not sure if you find another signal where it actually then causes this catastrophic failure. So indeed, this lower alpha made the age change more slowly. Right? So if you have some computational dissimilarities between encoder and decoder, these affect the computation of age less because we have more damping here. Right? But we are not really sure if it won't happen again. So maybe it's worthwhile to look for an alternative fix.
Using another signal.
Well, the signals are given to us. We have no choice.
Changing this 10, maybe.
Which one?
The 10.
The length of the field.
The length of the field. Yeah, it might work, but then again, you're not sure if it really fixes it for all the signals. Right? It's the same as with alpha. This alpha gives you some robustness because it updates the age more slowly, but there's no guarantee that it won't happen again, because it shows that the cause here is basically slight rounding errors in the computation between encoder and decoder. And these rounding errors are there, and they probably depend also on the signal that you have, so you don't really know if it happens or not.
Maybe if we found some adaptive way to change the alpha as the signal is being.
Yeah, actually, in principle, this is, I think in general, this is a good idea to adaptively change alpha. It's just a question how you would change alpha for if you encounter instability. Because if you encounter instability, then it's usually too late because the encoder has a fixed alpha and the decoder cannot say the encoder now change it to some other value. Right? So in general, it's a good idea. It's just not clear how we would apply it here.
Maybe in time intervals, and maybe also in varying time interval, you check the signal to error ratio, and if it changes to, if it gets lower, you change it to the one direction, if it gets higher to the other.
Yeah.
That you have to try out.
Possibly. What about fixing the underlying cause? The rounding errors between encoder and decoder. I mean, we know the cause, which is basically the computation. Some digit in the end, there's a wrong result, a rounding error from the computation. So how about fixing it? So how could we fix it?
Maybe by using the floor function.
How would you do it? I guess you are onto something, right? Basically, we need a precise definition of our operations here, of the computation. So we could use some other computation. Instead of a star, we could use some float in Python, some defined float. But actually there's also a quite simple solution, and this is basically avoid those very precise computations and introduce quantization. So quantization basically forces the encoder and the decoder to limit the accuracy of the computation, and hopefully this limited accuracy, including quantization, is then really the same in encoder and decoder. So that would be actually my next step. So here we have our code. Yeah, so as I mentioned, the error is bigger than in the LPC case. Oh yeah, we can also try what happens if we use the factor of 2. That might also nice. So instead of here, Did you want to have a 2 or a 10?
2.
Okay.
Okay, we can try out 10. Maybe the difference would be more clear.
Okay. So we use 10. And 10.0 here. And then we let it run. Did you see the message here with the encoder H? What does it mean? Not a number, right. So why is it not a number? You can see it. Original prediction error. The prediction error exploded. Right. And this not a number usually appears when you have an overflow. Right. When you have a very large number like 10 to the 99th and then you multiply it with 10 to the 99th, then it's overflow. Right. It's outside the representable range of Python. So that means here it exploded even earlier. Right. Before the sample number 4000. This is the reconstructed. You can see now it only lasts until sample number 2500. So it exploded much earlier than before. Yeah, this is what's left. Right at the beginning. So 10 is not good. So we go back to 1. But it's interesting to see, right? So here you can actually see what can go wrong with such an LMS coder. Yeah, so here the encoder for alpha equals 1.0, at least the predictor in the encoder worked fine. Right? Unlike for alpha equals 10, you could see that it was overshooting so much that even the encoder became unstable. And that can happen, right? As I mentioned. There's no guarantee that this method converges. So here's the decoder which we just saw. And here we see the sensitivity of the decoder for errors. In the code for the decoder in the LMS update for the predictor H, correctly we need xrec instead of x, since x is not available in the decoder, right, which we didn't do. So the slightest computation error, for instance rounding errors, are sufficient to make the decoder diverge and stop working after a few syllables of the speech. And this is what we just observed. So let me explain the first sentence. So you can see here for the update, we use X reconstructed, the xrec, right? Because this is what the decoder has. So strictly speaking, for the encoder we would need to do the same, right? We would need to use the same xrec also for the encoder, which we didn't do. Right? Here we use X instead of xrec. So strictly speaking, we would need to have a decoder in the encoder to make sure that both have the same basis for computing H. Make sense? So we really need to be careful that this computation is identical between encoder and decoder. So this should be xrec. We just assumed that it's the same because we didn't have any quantization. If you introduce quantization on the way to the decoder, then it's becoming obvious that this X is based on the non-quantized values and the decoder has reconstructed values based on the quantized values. So, right. So we see that the computed prediction coefficients differ in the last digits between encoder and decoder, which is enough for increasing divergence between encoder and decoder until the decoded signal explodes, becomes huge from instability. Right? If it starts with a small error, it will continue. It shows that the LMS is very sensitive to transmission errors. To avoid at least the computation errors, we need to include quantization in the process. At least some quantization. So here's the process with quantization. So here you can see our predictor again, right, based on past samples. But instead of using directly the input, x, right, we use the output, the prediction error, and reconstruct the values like the decoder is doing. So here you can see we have quantization, dequantization, and here this forms a decoder in the encoder. So this uses the quantized, dequantized prediction error values, put it into this decoding loop here, and then uses the reconstructed values from this decoding loop for the prediction. So then this x hat is the predicted value based on the decoded values. Makes sense? So here you can see, basically in the decoder, you would get the reconstructed value here at this point. Right? So here you have the error plus the predicted, and then this is the reconstructed value in the decoder. And you use the same predictor here, so here's the predicted value, and you use the subtracted from the correct value. So this is basically the decoder in the encoder. This piece. Make sense? Yeah, and this means we can now include quantization. Right? Quantization of the prediction error. In order to make sure the encoder predictor works on the same quantized values like in the decoder, it uses the decoder in the encoder structure. And this produces the quantized reconstructed value q of x of n. The function q here includes both quantizer and dequantizer. So q is our quantization symbol. The decoder stays the same except for the dequantization of the prediction error in the beginning. So here we have our index from the quantizer. Here we do the dequantization, and then we have the usual loop here. Right? So the decoder doesn't really change. Yeah, and here we see the reconstructed signal x is the same as for the encoder, plus the quantization error from the quantizer. So here our reconstructed signal is e plus x hat, and this is the quantized version. Yeah, and here's now the corresponding Python example for it. Here we have LMS with quantizer. So it's looking quite similar. The beginning is the same as before. We have our reading in of the signal, then E is the initialization for our prediction error. Here we have now a array for the reconstructed value, which we didn't have before, because here we have our decoder in the encoder. P is the predicted value, L is our prediction order. Here we have the array of our prediction coefficients. We start with some zero initial point. Then we have a quantization step size here. I choose the quantization step size to be 1/100th. So remember we have the range between -1 and 1. So that means we have 200 steps, which is actually not so much, right? So this is big enough to become audible. And that's also why I did it. I wanted to make it audible. Right? We can actually make it much smaller, it still works. But to make it audible, I just put it to this value. Yeah, again, we put here, we print the values of our coefficients and the error. Actually, for Python 3, there should be brackets. Like this. Here I'm computing the predicted value, here as before. And then where's the quantization? Here. So here you can see, here's the quantization error. And this quantization error consists of first taking the difference, as before, but now I'm doing the division by the quantization step size and the rounding. So remember, this is our mid-thread quantizer. Right? And then I do the dequantizer right away and multiply it with a quant step. So here's the quantizer and this is the dequantizer. So now E is the quantized, dequantized value, which we would have in the decoder, which we now also have in the encoder. So here we're doing the reconstruction. This is the decoder and the encoder. Here the reconstructed is the error plus the predicted value. And here we now do the LMS update based on the reconstructed samples. Okay, so this is now the difference. We're using the reconstructed values that we also have in the decoder. We use it also here in the encoder. Yeah, so then we compute the signal to error ratio, and you can see turns out to be 28, so it's slightly less than without the quantizer, which was to be expected because we do quantization. But it's actually quite similar, right? So it's actually not too much loss here at this point. So actually quite a good performance. Unlike us going from with alpha to 0.1. Remember, with 0.1 we got stability, but we had a quantization error of only 16. Right? Here we have this error of 28. So there's not much loss here from using quantization. So this seems to be a good fix. Right? Quantization fixes stability, hopefully, we still have to see. And it also leads to a good prediction. Yeah, then we listen to the error, plot it. And here we have a decoder. So basically nothing special. Here we print the coefficients again. Here we do the prediction. Here's the reconstruction and the LMS update. And again, plotting it and listening to it. Yeah, then we can run it. Let me first open it with Python, so with P8. So, gedit. Yeah, so this is basically the same that we just saw. And I also have the brackets here, that's good. So this should also run with Python 3. So let's try.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
It's okay. Well, could you hear the quantization error? So there was some noisiness. And you can also see it here in this picture. Here, right? So you have some constant noises, and you see the jumps which correspond to the quantization step size. Right? So here you can really see those this discrete behavior which comes from quantization. So you can see it, and you could also hear it slightly in the prediction error. So then the reconstructed. Here's the reconstructed signal, looks good.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
It also sounds good, right? Except for the quantization noise. Could you hear the quantization noise? So we can actually get rid of the quantization noise if we just reduce the quantization step size here. Say, go to 0.001.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So here you now can see larger. You don't really see the steps anymore, right? Those discrete steps, they're basically gone. Because now I have 2,000 steps for the quantization. And here's the reconstructed.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Could you hear noises? They're gone, right? And it still works. So that's nice. So we have high quality and stability. So that's kind of nice. So come back here. Oh yeah, we can also check our quantization coefficients. Let's see. So this is the decoder age minus 0.06176. Memorize it. 6176, 276. And here's the corresponding in the encoder. So 616, 6276. Identical. Up to the last digit. Right. Can you see it? So this is how it's supposed to be. They should be identical up to the last digit. So that shows that it works. Yeah, so first the prediction error increased somewhat, not so much. And the signal is now fully decoded even with quantization, although with a little noise, which has to be expected. But we can avoid the noise by reducing the quantization step size, which I just did. Yeah, and also observe that the structure for decoder in the encoder also applies to the other prediction methods. Right? So in general, you can apply it also to other methods. Yeah, and I guess that's it. Questions at this point? Prediction makes sense? Okay. So then, thanks for the attention and have a nice rest of the day.